bit more. Oh, look at that. You can put a little bit more. And then
Sprinkle iron filings over a bar magnet and you can see magnetism.
What is happening as he drops them?
The magnetic field is not uniform. It has invisible magnetic lines looping out of the top and bottom of the magnet.
Look at those beautiful magnetic lines of force.
The Earth is a little large, but if you could surround it with iron dust, you'd see the same loops of magnetic force. Like all magnets, the Earth's field lines converge at its magnetic poles. It is this field that protects us from cosmic radiation.
The sun, being a big, powerful star, is constantly ejecting a rather powerful stream of charged particles that fly through space. And were they to hit the planet Earth, the radiation that they caused could damage us, could give us skin cancer, cataracts. The Earth's magnetic field channels those charged particles and acts as a barrier to prevent them from striking the atmosphere. However, the Earth's field dives in to the atmosphere at the North Pole and the South Pole. When those charged particles hit the atmosphere, they ionize it, they make a weak plasma like we see here.
Plasma, a superheated gas in which electrons are stripped from their nuclei.
And it's those sheets of plasma that you see, that rippling, beautiful light that we call the Northern Lights.
These curtains of light lived in the legends of the people of the North. The Inuit in Alaska thought the aurora borealis signified celestial battles. To the Chukchi people of Siberia, the souls of their dead lived on in the light. Far to the south in the heat of California's Death Valley, the history of the Earth's magnetic field is locked in layers of rock. When rock forms, some of its magnetic particles line up with the planetary magnetic field. By cutting samples from the different layers of stone, researchers can show the Earth has had the same magnetic alignment for 700,000 years. But hit a layer lower than that, and the rocks reveal that there have been times when compass needles would not have pointed north.
And one of the strangest things in geomagnetism is the magnetic reversal. The idea that the entire planetary magnetic field can come discoupled from the rotational axis. Instead of pointing north, the magnetic field might be pointing east for a while, and then reestablish itself, and your compass needle will point south.
Death Valley is an ideal place to learn about magnetic reversals.
There's an active fault zone that runs through the bottom of Death Valley here. It has taken these lake beds, turned them on end, thrust them up, and then the streams have dissected down through them, so we have almost 100% exposure. One of the few places where we can go and say, right, the magnetic field started in a normally magnetized state here, and 3 or 4 meters up there, it's in a discretely reversed state. And yet what we're recording is the history of the Earth's field. Each little bed, when it is formed, preserves precisely the magnetic field at the time.
Core samples are analyzed in a magnetometer to determine the strength and direction of the magnetic field. Researchers can use that information to plot a geomagnetic map that tells the history of the Earth's field reversals. Far from Death Valley, there are other reliable places to study geomagnetism. Volcanoes. Molten magma erupting from the Earth's inner chambers is rich in iron. When it cools, it locks in clues not just about the Earth's magnetic field, but also about how the continents were formed.
And so if I have a liquid magma that comes up and then gets in place, solidifies, and then cools, those grains become magnetic. But the important thing is, as they become magnetic, they lock in their magnetic direction parallel to the Earth's field at the time.
Beneath the surface of the ocean, cooling lava locks in magnetic information as it creates new seafloor. Over millions of years, a stripe pattern forms, creating a timeline of the Earth's field reversals. These patterns tell geologists that as new stripes form, the continents are pushed apart. This observation led to a major breakthrough in understanding the way the Earth works, the theory of plate tectonics.
There's no parallel in the history of science where one set of observations made such a key change in the entire field and turned everything. Perhaps the only one that's comparable, say, is the Darwinian revolution in biology, which still has its ramifications. But the plate tectonic revolution was a similar thing in geology, and that was driven by magnetism.
Whether on the sea floor or in Death Valley, magnetic stripes also hold clues about when the Earth's field might reverse again. Studies indicate we are in a period when the magnetic field is declining fast, 15% since the year 1670. If the present trend continues, the Earth could lose its entire magnetic field in about 2,000 years. Compasses would be useless, the northern lights would vanish, and our globe would be exposed to cosmic radiation. But no one can be sure if this will happen. The magnetic field could also reverse its trend and begin gaining strength, keeping intact the magnetic world we've come to depend on.